Hi everyone, today we will discuss one of the important techniques which is used to understand construction materials, and that is calorimetry. So just to begin with, what does second law of thermodynamics say? Change is inevitable, right? Basically everything naturally tends to its most stable state, right? So some materials benefit from the change, okay, becoming more useful, right? But for most materials what happens, change presents reduction in useful properties and loss in quality. So for many materials around us, change can be obvious, right? Like discoloring of paint for an example, rusting of metal you have seen, etc. Like other changes can be subtle, not as obvious, you can't see, right? Such as polymorphic changes in crystal, right? Fatigue in metal, surface absorption of vapor for an example. So in majority of cases, change can have a considerable influence on the useful properties of a material. So calorimetry has found its value for recognizing these subtle differences, which you cannot capture using any other technique. So basically calorimetry can quantify change in terms of rate, how much, and the probability of a change to occur. So we are talking about change. What kind of change? So why calorimetry? That is the first question we have to address, right? So calorimetry is nothing but the measurement of heat and heat production rate, okay, and it is used to study processes ranging from physical, chemical and biological, as they are all related to enthalpy changes. As long as there is enthalpy change, there will be heat signal coming out of a system, and as long as we can measure that heat, we can use this technique. So basically calorimetry is made of calor is a Latin word, calor is heat, metron is a Greek word, means measure. So it is a measurement of heat. So when you hear about calorimetry, first thing which should come to your mind is measurement of heat. So in this lecture what we will see how it was developed, right? It is very important to know the history, where we are and how we come to where we are, how the technique was developed and what is it about, and what are the applications, because that is also important to know where it can be used. We will look into the variety of applications, then we will focus on its application to understand construction materials like cement for an example, mortar, concrete, okay. So the history, if you check, calorimetry has been used to study the reactive systems since 1780. So long time, more than 200 years ago, right. Reactive system, please pay attention to the word reactive, as long as there is some reaction, because we are talking about change, right. So it has been used to study reactive systems, right. So what was the first, if you look at the history, what you find that it is very interesting study by Lavoisier and Laplace. They were the first ones to develop this ice calorimeter, okay. And where did they use it? They studied the respiration of a guinea pig, right, in an ice calorimeter. What was the principle they were studying? Basically they were looking into thermodynamic and kinetic evolution, right, by estimating the quantity of water collected. So it is about guinea pig respiration, right, when as long as there is a respiration, it will melt the ice. So they were quantifying the water which was being melted, right. Also the rate of melting, try to understand two things. One is the amount of water which is formed through melting, and also rate of melting, very important. So that was the ice calorimeter these people used, right. So basically they were just measuring water, right. Obviously you need a good balance. So Lavoisier, their study was restricted to measuring exothermic reactions. You are talking about the exothermic reaction, means the heat is released and that is used to melt the ice. And the sensitivity of that instrument was dependent on the accuracy of the weighing of melted ice, right. So that was their experiment. Interesting, right. They were just, it is also interesting that how this simple experiment can tell you about thermodynamics and kinetics. But now things are different with the advancement of technology, right. We can measure signals in the order of nanowatts. So here what you see is a calorimetric signal showing the sensitivity of an isothermal calorimeter fitted with nanowatt amplifiers, right. So in this experiment was performed at 298 Kelvin using 3 cubic centimeter glass ampule, right, containing 1 gram of dry talcum powder. And then what happened? When they put 50 nanowatt electrical input, right. So you see it is around 50 nanowatt, right. The point is you can measure the signal, this is nanowatt axis, right. So within second you can see, right, you reach in around 50 nanowatt, it is maintained because they maintained this for 1 minute, right. So the idea of showing you this is that we can measure the signals in the order of nanowatts. That is the technology we have currently, right. And so basically then we can measure very slow reactions where we which otherwise would not be possible to measure, right, because if you have a signal in microwatt order, that is also very small. That is what we will focus on, like as far as construction materials go. Little bit about, so far you know that where can we use this calorimetry, right. As long as you can measure the heat, you can use this calorimetry. But what can you get, right? What do you get from calorimetry and how can we use it, right? That's the goal of this slide. So let's see. All of you know thermodynamics. What does first law of thermodynamics say? That the change in the internal energy of the system is equal to the heat energy which you put plus work done, right. Delta U equals to Q plus W, where U is internal energy of the system, W is work done and Q is the heat energy added to it, right. Now if you talk about the constant volume, right, in constant volume your work done will be 0, right. So your du, this is change in energy, can be related to this change in heat at constant volume, which equals to Cv dt, right. Cv is the heat capacity at constant volume. You must have seen this in your basic courses, right. Similarly, if you look at the constant pressure, so enthalpy H is equal to U plus PV, right. Now change in enthalpy dH, right, can be related to change in heat at constant pressure, right, equals to Cp dt. Again these are basics, but what I mean to tell you here that please notice this term. So what I am saying is like you can get this enthalpy. Enthalpy is coming from a process, whether the process is physical, chemical or biological, and all you have to do is to measure this Q, the heat, right. So basically the change in enthalpy, which is delta H, right, can be related to this power output, because the calorimetry you are going to get these two signals P and Q. What is P? P is nothing but thermal power. How do you measure power? Power is the units of watt or joule per second. So you see here power in joule per second, can be equated to delta H, which is enthalpy, will be joule per gram times this rate K for an example. It tells you about the kinetics, right. You see the units are gram per second, how fast the reaction is happening, right. So, thermal power is P, and you can also get Q, this is the total heat, by integrating power, right, over the time period, right. This is the total heat which is released during a process. Obviously, it will be equal to delta H times M. M is the mass, because delta H is joule per gram, you can see, right, times mass will give you total Q. So, from calorimetric measurement, you get these two quantities P and Q, right, and by knowing P and Q, you can get delta H, right. You can get K. K is kinetic rate law. It tells you how fast a process is taking place, whether it is a decaying process or it is something else, right. So, basically you can see here how powerful it can be, right. Just by measuring, having these two measurements, you can tell a lot about the system. Any process, if it is taking place, you always want to know how fast it is taking place, right. For an example, think about rusting of a metal. You want to know how long will it take, right. Also you want to know what will happen after, suppose 5 years, 10 years, how much material would have degraded. So, that you can only find out when you know this K, which tells you about the rate, right. So, idea is you can get to know thermodynamics and kinetics both. Clear? Now, we will look into some interesting applications. So, now you know the basics, you know the calorimetry is nothing but measurement of heat, right. It could be heat rate, could be total heat. Also, you know what do we get from calorimetric signal, right. Very interesting applications again are these, okay. So, start with the milk fermentation. Can you imagine that isothermal calorimetry, for an example, can be used to understand milk fermentation, right. So, because the microbiological fermentation produces heat, right. As long as there is heat, does not matter where it is coming from, that is the idea. So, one can, for an example, map the properties of microbial culture. For an example, assess differences between different cultures, measure their doubling time, how fast they grow, and look at the influence of additives, because we are talking about the fermentation. So, we are interested in another example could be microbial spoilage prevention, right. So, the general goal of preventing microbial spoilage can be reached by many methods, like you can use natural and synthetic chemical preservatives, right, and thermal treatments. So, isothermal calorimetry can be used to study the effect of such methods by studying samples treated with different methods or measuring the thermal power before and after the application of method. You want to study the effect of something, so you can carry out this study, right, and see what happens when you suppose use an additive, what happens to the heat signal. Cell death from blanching, all of you know what is blanching is, right. Blanching, suppose in cooking at least, what you see, like you have spinach, you put spinach in hot water, suddenly you lose, you see color in the water, then you remove the spinach, right. So, it is a blanching process, right. So, that is also calorimetry can be used to quantify basically the cell damage, and when you are doing that, you are doing you are causing cell damage. So, increasing intensity of heat treatment, for an example, progressively reduces the number of viable cells in a tissue sample and results in a corresponding reduction in the rate of metabolic processes, right. So, the blanching process can be optimized, right, by the use of calorimetry, right. Similarly, you can use it for wound respiration, right. See the commonality between these applications, like as long as there is heat, does not matter where it is coming from, you will be able to monitor the process, right. So, it is well known that when you cut a vegetable, right, it causes the cell damage, right, and which sets off several different protection and repair process in the non-wounded cells, right. So, calorimetry can be used to study the effect, right, of wounded area, right. One can use this to investigate wound induced processes and how the rates of these can be reduced, like to prolong shelf life and decrease of flavor, right. These are some of the things. Shelf life of foods, that is very important, right. You want to know what is the shelf life of a food we use on daily basis. So, calorimetry is a potentially useful tool for shelf life predictions, right. Several attempts have been made in this direction. For an example, this isothermal calorimetry has been treated as a method to detect microbial spoilage, right. You want to know when things spoil, right. For an example, spoilage of meat, eggs, carrots, right. So, by quantifying this spoilage, microbial spoilage, shelf life can be estimated. These are some interesting applications I just wanted to draw your attention to, which will motivate you further to use this technique, right. So, this can offer a solution in terms of quality control of food. You have a food, you want to know the shelf life, there is always something written the backside of any item you take, food related. How do you determine that? You can use this technique, right. What do you see in this plot? Okay. What is in this plot? We have this result indicates that the green tea, so basically you have this only carrots. Suppose we are interested in the shelf life of carrot juice, only carrot juice. So, you have this signal, right. We are trying to enhance this shelf life, we are trying different things, adding different things. What do you see? 10% green tea, it does something, but the effect is not that much, right. What do you see? Basically in sodium benzoate significantly slows down the process, right. So, like the high doses of sodium benzoate significantly delays the onset of growth, but it does not completely prevent all microorganisms from growing. You can see still you are getting some heat signals, but at least you are delaying the process, right. So, what type of microorganisms that are present in the juice cannot be inferred. We can't tell what kind of microorganisms are there. We only can see that microorganisms, the process is getting delayed. But calorimetry is in many cases an ideal method to start a study, right, which with as it gives a general overview of how fast processes take place and what factors that control the process rates. It is all about rates, how fast the changes are occurring. So, you can at least say now that when you have sodium benzoate, you are delaying the microbial spoilage. So, basically any process, whether it is physical, chemical, biological, right, can be monitored. So, if you think about the physical processes, right, what does come to your mind? For an example, crystallization, right, crystallization of amorphous materials, for an example, right, can be studied using calorimetry. A useful method for analysis is to couple a heat calorimeter where you can get the signal, right, with a vapor perfusion device. You also want to induce some changes, right. So, in this case what you can do, you can change the partial pressure and that can be used to change the degree of amorphousness, or you can induce some crystallinity that can be monitored using calorimetry, right. Another change is morphological changes, like we talked about polymorphs, right? Crystals have different forms, right? A number of polymorphic forms of crystalline material is dependent on how many different orientations the molecules can be arranged to form a crystal lattice, right? It's all about the arrangement. So, the molecular arrangement of molecules in a lattice can have significant effect on the physico-chemical properties of a material. So, calorimetry can be used as a method for identification, right, of polymorphic forms by exploitation of differences in physical properties, because when you are inducing these changes, you are changing the physical properties, and by exploiting the differences in that. Hygroscopicity, right? Hygroscopicity, calorimetric investigation into hygroscopicity typically involve RH perfusion, means you change the relative humidity and you see how much sorption is taking place simply, right. So, a material is subjected to increasing levels of water vapor and the mass increase followed by measuring the associated enthalpy change, right. These are some physical processes. We have not talked about biological processes for an example. So, it can be also used to study the biological processes, right, as long as there is heat signal, right. So, idea is to see the application of calorimetry in various different fields. So, very commonly used to study protein and protein ligand binding energetics, very important in pharmaceutical industry, right. So, biological systems evolve and are maintained in accord with the laws of chemistry and physics, right. Indeed, at molecular level, what happens? Highly complex biological processes can be regarded as variations of non-covalent and covalent interactions. So, thermodynamics reveals the essential energetic principles of biological phenomena. It provides general formalism for describing a system in terms of its energy. So, calorimetry can be again used to quantify the heat effects accompanying association between molecular entities. Similarly, enzyme kinetics can be studied. Enzyme kinetics, right? Enzymes are macromolecular biological catalysts, right, that accelerate chemical reactions. Now, the molecules upon which enzymes may act are called substrates, and the enzyme converts the substrates into different molecules known as products. So, all the metabolic processes in the cell need enzyme catalysis, right, in order to occur at the rates fast enough to sustain life. So, the rate of enzymatic reactions is proportional to the heat flow, again associated with the formation or breakage of chemical bonds. In these all processes, what is happening is that you are getting heat signal and you are measuring it. That's the point. Okay. Drugs design. So, see, you may not have thought that it can be used for, so it can be used for drug design, because calorimetry follows the heat change when a test compounds. We are in drug design, what we do, we test different things, right. So, when a test compound binds to a target protein for an example, right, so it can be again used. So, it allows precise measurement of affinity, its affinity, what is the binding affinity for an example. So, the calorimetry in the presence of other ligands rapidly provides information on the mechanism of action of the test compound, identifying the intermolecular complexes that are relevant for structure based design. Only idea is to draw your attention to these different variety of applications, right. I mean, we are not going deep in bio and other things, but just so that you appreciate this technique, right. Similarly, we can use it to understand chemical processes. Now, what kind of processes we are talking about? For an example, acid base titration, right, all must have heard. So, we can use calorimetry to study acid base titration. Also, we can determine enthalpy of vaporization of solvents. You want to know what is the enthalpy of vaporization, right, it is also a chemical reaction. Finally, we can use it to understand cement hydration, right, because the reaction between cement and water is also a chemical reaction, and you know that it is an exothermic reaction where you release heat, and if you can measure that heat, basically you can study the cement hydration. So, in this lecture we will focus on cement hydration, but you can see that it can be used in all processes, whether they are physical, biological or chemical, right. So, it is a very useful tool.